Let's get started. Hi, everyone. Thanks for joining the C3 AI DTI seminar series for the spring semester. My name is MBSE Wu. I'm right now a postdoc at Berkeley EECS, and I'm also a research fellow at Simons Institute. I'm co-organizing and co-hosting this seminar series with Professor Sastry and Professor Srikant in this semester. C3 AI DTI features research that focuses on studying how artificial intelligence, machine learning, and big data can lead to scientific breakthroughs with large-scale societal benefits. Here, we acknowledge the support from our academic and industry partners. We are very excited to announce that this spring semester series has a special theme that focuses on a very important topic on incentive design and learning for societal systems. We have some really great speakers already scheduled to give a talk, so this is definitely going to be a fantastic series. You can find more information about the past and future speakers, as well as the talks on our website. We also provide the past talk videos on YouTube channel. You can subscribe to our newsletters and our channel so that you don't miss these talks. Now let's welcome today's speaker, Professor John Baras. He's going to present his work on a fresh look at design, a rigorous framework for integrating model-based and data-based systems engineering. I'm going to give a brief introduction of Professor Baras. Professor Baras is a distinguished university professor at the University of Maryland, College Park. His research interests include systems, control, optimization, autonomy, machine learning, artificial intelligence, and communication. He received his PhD degree in applied mathematics from Harvard University. He holds the Lockheed Martin Chair in the Systems Engineering. He is the founding director of the Institute for Systems Research. He also co-founded and directed the Maryland Center for Hybrid Networks. Professor Baras is a foreign member of the Royal Swedish Academy of Engineering Sciences, a life fellow at IEEE, and a fellow of many important academic groups and societies, including SIAM, AAS, NAI, and others. He has won numerous prestigious honors and awards that includes the George Axelby Award, the Leonard Abraham Prize, the Simon Raymond Medal, and the Richard Bellman Control Heritage Award. In 2016, he was inducted into the Innovation Hall of Fame at the University of Maryland. Without further ado, let's give the floor to Professor Baras. The talk will be 15 minutes, and for the audience, please use the Q&A feature to submit your questions, and we will ask them on your behalf. John, you can start sharing the screen now.
Yep. Thank you. It's wonderful to give this lecture even remotely, although I was in Berkeley the last 3 days. So, the topic is going to be some summary of work I've been doing over the last 10 years and some recent new challenges that we face. And it has to do with something that's a very important problem, no matter what system you are dealing with, which has to do, how can I synthesize complex systems in such a way so that I can have some guarantees that they're going to behave as designed, what we call systems engineering. And one of the efforts that we have been doing in the Institute for Systems Research at the University of Maryland is try to make systems engineering a science and quantitative. So let me start. You all know that we are facing this kind of complex problems most of the time in this 21st century. They go all the way from smart grids to medical instruments to human and social networks. And I call this the next wonder, because what model-based system engineering or model-based engineering is about is how can I conceive something, an idea, and make it into a device or a service. And the new challenge has come around the last 5 years, where now we have to ask, can we integrate model-based methods with methods from data? And that means artificial intelligence and machine learning. And that's one of the things I want to discuss today. So where I started on this was in 2003. I gave this talk at Maryland about the impact of information technology in engineering. And I said that there are two ways that information technology impacts engineering. And I want to go through them quickly with you to see that the story hasn't changed much. The one was the devices. We have lots of devices that go everywhere, in buildings, in watches, in instruments, and so on and so forth, right? In cars, in sensors for the body. And the other one is in tools that we use to design things. And of course, the best success here is the way we do VLSI, like when we do the cadence tools, we do schematic capture, and then we go and make them. And out of that came the understanding that when you describe a system, and that's something that is neglected a lot in control systems, is that I have to talk about the structure of, which means what the system consists of, and the behavior of the system, which is what the system does, okay? And the mapping of behavior into structure is something very important. So when we try to see if there is anything as close to VLSI as other areas, there isn't. Even in MEMS, we cannot do what we do with VLSI, which is the closest cousin. That's my electromechanical systems, okay? Now, let's see on the other side what happens. If we go to biology, we have an existence proof because we have the DNA, then the DNA tells us how the bases go together, how they collect to make small molecules. And that's a nice picture that I got from NIH, and you get the whole organism, right? So there's a fully programmable automatic assembly things for biological systems. And that's a nice movie that you can also download from NIH and tell you the story. Let's look on the other side. So I have schematic capture. Okay, I have a reasonably good system for VLSI, and then let's see what happens on the manufacturing side. This is a reasonably old picture of a manufacturing factory where you produce chips. And what happens there is that we were able to actually describe what we want to design with the program, send it to a foundry, and we'll get back a chip, right? Which is actually revolutionized microelectronics. But if you compare the two, we are far apart, okay, between what we can do and the existence proof in biology, okay? All right, so let's go further. There are some other things that I mentioned in that talk, is that in electromechanical systems, basically you do different programs and you connect them almost by patching, okay? And then I show you here a wonderful invention, which these small chips that they have many, many mirrors, that they now are a part of copying and most importantly of TV. These are the, it's called digital light. This was an invention that came out of Texas Instruments. And these are at micro scale, okay? And they had to actually rethink how to design them, and they had to rethink their production lines because they were problematic in terms of creating them to be sustainable. And then you can compare, how small these things are with a very small aphid on a micro mechanical device of this type. We do not know how to design these things as well as we do VLSI or even at all. And then there's a question of, how we actually relate the cyber and the physical or the bio. And we have all kinds of interesting thoughts here. You can get inspiration from biology about how things are connected in what we call today biological computing, and then you make things to grow, et cetera, and there's languages that have been created, which actually were inspired by some of the things I'm going to talk about today, and then you get into complexity of this type, which is a very small part of a cancerous cell. Okay, and so you have many things you can learn from biology, and vice versa, which we do all the time. And then you also have to worry about what computing means. There is a very nice society that I belong to in the internet, which is called Physics of Computation. And the point they make is that what you mean by computation depends heavily on the physical implementation of the computing devices. And you can go back to abacus all the way to quantum today. And then you go even further to things like how you can do this famous experiment that we had at Duke some time ago, where the chimpanzee will think of grabbing a banana, and the signal will be transmitted to MIT, and a robot will grab the banana. So you can see very interesting multi-agent systems that they communicate and active and when they're apart. So we talked then about swarm intelligence, and now how come these simple organisms can do very complicated things. And out of that, my conclusion of that lecture was that we have to talk about this interaction between cyber, physical, bio. We have to try to understand how we synthesize the systems. And at the bottom line is that we have to completely change the way we teach people, okay? Because that what we teach is, in my opinion, still very archaic. And we had these discussions with people at Berkeley the last 3 days. So what happened since then? All right, so 777 were designed first by software, and nothing was constructed before everything was verified. And 787 even more so. We now, as you study in this consortium, that humans are integral parts of systems, okay? We have cyber physical systems. We have social networks over the web that they influence everything we do. We have economic networks over the web. We have renewable energy, smart grids. We have a lot of advances in the human genome. And we have multisensory environments, monitoring, autonomous and connected cars, okay? Cloud computing, big data, health information technology, okay? Internet of Things. First printed car. Actually, in China, they tell me they had to print the house, okay? Crowdsourcing and manufacturing, all right? So you can see that the complexity of systems, it's increasing. So this is a very nice paper that you should read from Proceedings of IEEE that described how revolutionary was the design of 777 in terms of synthesize everything by the tools and then going and building the screws and other things that you had to build. And then we get to 787. What is interesting about 787 is that Boeing dared to construct a wing by composites, and everybody thought they were crazy. But they did it, and not only worked and they produced more efficiency like you see, but they were able to show that this can take off and land in smaller space. So there's a very simple example of where the physics of the design can influence the cyber or the thinking of the device, which is the control. Then, of course, you know the iPhone, which is a very complex system. It has about 800 components. And I remember when the CEO of Qualcomm gave a lecture in Maryland, okay, Irvin Jacobs about that. He said, this is the device that eventually will do everything. And you know that this does it today. Okay, how do we design these things to make it easy? Then we have smart cities, smart everything. Okay, that means that things are connected by networks, and we have all these things that you see here. And we have things that we design and things we did not design that is consequence of these systems. How can we understand these things? Then you have the so-called, network embedded world. You have the devices you all carry, more than one. You have the cars that are connected. You have transportation that are connected. In the lower picture, you see a medical system that Qualcomm had where they can follow your heart and tell you if you're taking your medication, so if you are in trouble, and so on and so forth. I can go on forever in this. And then, of course, you have cyber physical systems in which, we started around 2008, and now it's a very big area, and it affects many, many, many areas. Okay. So what's the challenge here? The challenge is that how do I control this complexity? Okay. And one answer is I do what we do traditionally in engineering, divide and conquer. How do we do that? How do we divide components and put them together and we have some understanding of quantitative understanding of how well they satisfy requirements. Can I ask questions like what if? What if I change the battery to this? What's going to happen to the car? If I change the brakes to that, what's going to happen to the car? If I change these medical instruments to this sensing, how much better I'm going to do in terms of detecting a disease and so on and so forth. And in our institute, when we say systems engineering, we talk about the full life cycle of the system, meaning the design, the manufacturing, the operation, and the retirement. And every one of them has challenges. And we need to do several things here, which I will describe. And we need to be able to integrate many things and many domains in a way that some people say it's very difficult or impossible. We humbly disagree, and I'll show you why. So we identified 4 challenges in the work we've been doing in developing a rigorous model-based system engineering and framework and the associated mathematics and algorithmics. One is you have to have the ability to create integrated modeling hubs, as we call them, to incorporate different physics and different logics. These are now called digital twins. Second, we have to be able to link these hubs with tools which are quantitative to understand trade-offs. with different metrics and different constraints. And this is called design space exploration. And then we have to link these two integrated things, the modeling and the trade-off analysis, with databases of components, which may go over many years, and where components may be represented by different methods, by images or programs or other things. How do we link to that? That's still open. And then we have to basically handle the requirements. We have to go from things you state in your language to mathematics, which are typically are either rules or constraints or metrics. And how do we actually trace this? How do we organize them hierarchically? And how in the end we verify and validate what we build so the customer can accept it, or you, the designer or the operator, can understand that it's operating as expected, which actually is a version of trust that we deal with. So that's a slide from my good friend Albert Benveniste from IRIA, where they study these kind of problems. And the first thing you realize is that in a car, there are many, many different physics, each with their own logics and rules. Okay, and that's another slide on the same topic with my other collaborator, Janos Stepanovic from Vanderbilt. And you can see that in several of the systems, you have mechanical, electrical, hydraulic, thermal domains. How can we put all this together without getting completely lost in this complexity? But it's not only the physical domain. We have different logics. We have different logics for the plant dynamics, for the controller, for the software, right? We have software that they are totally Boolean. We have software that they are algorithmic in terms of calculus, like mathematics, I guess to say. They're different architectures, okay? So here is one of the important slides that we teach. This is what we call our model-based system engineering process, and I'll go through it. We started developing this with General Electric many years ago. You start by collecting information about what is the system that you're trying to build. Then from this information, which typically is text, you try to create two block diagrams. One is the structure diagram, which tries to answer the question what the system consists of. The car has wheels, chassis, steering wheel, radio. And the other is the behavior diagram, which is what the system does. Most control people study that. This is differential equations, integral equations, finite state machines, and so on and so forth. But you need both. In some of the more older types in controls, like myself, we used to do that. We used to understand if you're going to do even a linear time invariant system and you choose the hardware, which is the structure, that has certain implications. Okay, this has been forgotten a lot today. And then you have to ask yourself, you have to map behavior into structure. You have to ask the question, for a particular scenario or behavior, what parts of the structure they get involved? When you brake in the car, what parts of the structure of the car get involved? Okay, this is changing from the old cars where you push a pedal, now that the electronics are involved. And once you finish this, you have now essentially an architectural diagram, because you have a block diagram of behavior, a block diagram of structure, and they are mapped to each other. And now you can go back to your requirements or specifications and start allocating them to the different blocks. And you can translate them mathematically into constraints and metrics, and you are ready to do trade-off analysis and design space exploration, which you better do in a divide and conquer way, otherwise you're going to get lost, okay? And after you finish with all that, you have to do validation and verification. And you can do this either by experiment, which is expensive, or by some automation. What industry wants is they want about 75 to 80% of this to become automatically. Fortunately, the same mathematics you're using in trade-off analysis and satisfaction of these constraints also can be used for verification and validation. Here are some of the tools that we use. And you can see here some of the things that several of you have seen using, and we're putting them all together, all right, to try to do this. And one language you use is systems modeling language. Systems modeling language is a different language than UML. UML is this corresponding language if you write software. SysML is not a programming language. It's a language that helps you manage these models. And it has four fundamental components. It has a component that describes the structure in the block diagram. It has another one that describes behavior, which are like time diagrams of how the components interact over time. These were also there in UML. And then they added two more things, the requirements diagram and the parametrics diagram, to try to allow for these multiple physics and different requirements. So this, we call them the pillars of SysML, are very important because they allow you to start working on the three key problems that I described. And then there is this diagram which tries to explain the difference between UML and SysML. You had behavior and structure before, but now we added these other diagrams in terms of requirements and parametric diagrams. So one of the challenges that we're making progress, but we haven't resolved, is how can you actually link in an iterative way and at design time, the trade-off and design exploration tools with the behavior diagram, the structure diagram, the requirements diagram, and the parametric diagram. Because if you don't do that, then you don't solve the so-called Tower of Babel problem. You have a mechanical engineer, a computer scientist, an electrical engineer, and chemical engineer. You want to have a method by which they do their thing through their lenses, and the other people can see the impact of what each one of these domain experts did from their lenses, okay? And that's what we have with these tools. We can do that. And that tries to describe, is described in this diagram, where we have the SysML diagram in the center as an architecture diagram. And this is constructed in such a way so that you can actually easily link specialty tools. Like if you want to do control analysis and you like MATLAB, you can link MATLAB. If you want to do hardware, you can link with the hardware specification language and so on and so forth. So think of that as a key piece which allows you to connect different tools from your own organization or others and create this, at least this digital twin model, okay? And that's the second important slide that says, I want to integrate modeling tools up here, which we have done. And sometimes you have to use meta modeling, meaning models of models, how to connect them. This is pretty well understood now. And you have a lot of things from industry and companies like Siemens and Dassault Systèmes that allow you to do that, and ANSYS even. Then you need to link that with the trade-off analysis tools right here. And we have done this with connecting with optimization tools like Cplex or Groby or eLog, which is a rule-based system. What is not well done yet is what we can do with our own tool, which doesn't scale easily, where we want actually to do this trade-off analysis and interact at runtime. And then the open problem that I will describe at the end, what we're doing the last 2 years, is you are Raytheon and you're making a lot of sensors over the last 50 years and you store them in databases with different components. Can you give me a tool that I can search these databases to find if there is a component there that I designed some time ago with different representation that may be close to what I'm looking for my current design, okay? Because if you don't do that, no company will start from scratch doing all their designs and tools with however good are the new tools that you produce, okay? And then the toughest of all these problems, mathematically and otherwise, is how do you handle the requirements? You do the trade-offs and the verification and validation. So here we use all these tools. We use automata, timed automata, Petri nets, influence graphs, set value systems for reachability analysis. And you've seen pieces of that done in various parts of control and systems or in communication networks. How do you allocate requirements? How do you check the requirements? So here we use model checking. We use a logical structure that's called contract-based design, and we even quite go to things like Isabelle or Koch, which are automatic theorem proving. Okay? So the mathematics can get pretty serious, and the algorithmic side of these things is not trivial. And one of the challenges you face, and that industry wants, is you have to make it easy, because they tell to me, you know, John, I cannot afford to have 3 PhDs in front of every design stage. Okay. Now we've done that, and I'll show you how far we have pushed it. So let me go to some specifics now, okay? Let's take smart grids, okay? That's where everybody knows what smart grids are, and then how do you design both the structure of the systems and their controls and their security, okay? So the work I'm about to describe to you was done at a master's thesis in our Masters of System Engineering. So the student created the models I described using SysML, connected to trade-off analysis, okay? He used a meta-modeling language which was free from Europe, which was called Imoflon. And so we did everything I described to you. We used SysML, we used these diagrams and the time diagrams. We integrated with trade-off analysis tools, wonderful work, okay? And then because of the console of CAD, which was developed primarily by Professor Titz in Maryland, we could actually do runtime, all right? So here we use duality from optimization to try to tell you how the various metrics and constraints that you have, and they are the mathematical expression of your requirements, how close or bad they are to being satisfied. So by using this comb, all right, we can see red things and green things, and we can see which of the criteria are satisfied. At our runtime, we can find the worst one that is not satisfied and modify it. relax it or make it tougher and so on and so forth. And I can see, and now I don't expect to read all that. I'm telling you that to tell you that this is not abstract. There are mathematical expressions for this criteria, that they have this kind of metrics, operational cost, fuel, different variables. They can be even difficult timing constraints like this, because if I open up a generating unit for a smart grid, I cannot turn it off right away because it has to stay on for a certain period of time. And those of you who are in scheduling know that these corresponding problems in optimization are very difficult because they end up in mixed integer programming problems and other things. Of course, the problems that we did in this master thesis were modest. Now you have 10 times or even 100 times more complex problems in terms of design variables and the constraints. You can see that eventually you move at runtime where you satisfy the hard constraints, the soft constraints, and the program allows you in the end to go somewhere that everything is happy and you are satisfied by interacting via this design exploration and the model. So that was a very good success. And we are increasing that now to go to this kind of more difficult smart grid problems where you have now batteries, you have interactions with the utility or not, and so on and so forth. I'll skip that. And one of the things that, of course, we run into all the time is this compositionality. If you can direct, divide and conquer all the time, but you have a very important problem. You carry constraints and specifications for the components. How do you combine them back? Is your design composable? Okay. So we have two answers to this. One is inherent compositionality, which comes from the so-called models of systems that they under the name of port Hamiltonian systems. Now, the good news about port Hamiltonian systems is that any physics that any physical component can be modeled as a port Hamiltonian system. Even network systems can be modeled as a port Hamiltonian systems. They have been studied very well in control, and they can be used in many, many applications. The good news for us is that the language Modelica that lots of people use to model physical systems is actually based on a port Hamiltonian formalism. Okay, and these are inherently composable. I mean, if you compose port Hamiltonian systems, you stay port Hamiltonian. That's why we call them intrinsically composable systems. So that gives us an answer of how we can proceed, and we use that. You will see how. For those of you who are interested to see a little bit more math, that's what port Hamiltonian systems are. All right, they are these two matrices, J and R. One is positive definite, the other is Q-symmetric, and they can typically very good to model some kind of flow among the links of the graph of the network. This can be energy, this can be electricity, this can be information, all kinds of things. All right. So I'll skip this. We applied the same formalism that we applied for the smart grid to a problem that we work with people at Berkeley and United Technologies, which was the communication network aboard an aircraft, the power, scheduling, and control of that. And you can see this is a very complex system, but the same things we applied. And we have, again, metrics, which are equations like this, fuel consumption, procurement cost, and so on and so forth. And we do this design space exploration, okay? The same tools, okay? All right. And one of the things we learned doing these things is that we have to learn not just calculus mathematics, but also logic mathematics, and in particular, the way they apply in terms of satisfying constraints and trade-off analysis. So industry was ahead of the academics in this. That's why if you are following the IBM optimization workstation, they have linked together Cplex that they bought. This was a very strong industrial strength nonlinear optimization tool created actually by academics. And they also bought ELOG, which was a very strong constraint-based reasoning or rule-based system that from a company that came from France. And they linked them together in the field of communication networks because there first they had to do things like that at scale. Okay, so the second lesson here is when you do design space exploration, you have to be prepared to deal with tools that they use either multi-criteria constraint optimization or constraint-based reasoning. So this you can go back and forth between logic and optimization. Then we go to another field, again, to show you that it's commonality of method here. This is energy efficient buildings. These are real buildings. And what you see here is the architecture of the building being changed by engineering consideration for better energy. Like, for instance, they change, you see the way the roof is so that they can improve the airflow. One of them is in China and the other is in Chicago. Okay, so And this has led several schools now to bring together architectural schools with engineering to be able to bring the art of the architect and the thinking of the architect together with the quantitative methods of engineering. Okay. First time I saw a program like that was in the Royal Institute of Technology, Sweden, and now there are several universities that they have brought this together exactly to be able to handle this problem of energy efficient buildings, which are aesthetically nice, but also engineering well efficiently. This is a mock-up of a zero energy building we have at NIST. There are several others here, especially in California in the Lawrence Livermore Lab, where you can actually change the walls and so on and so forth and study various methods for creating zero energy, creating, for instance, using solar energy and the way the environment is and so on and so forth. We analyze this again in another master's thesis, where we model this by something which is called Energy Plus. Now there is a modelic version of the Energy Plus, thanks to a national program that finished, I believe, 2 years ago. And the reason that we needed to go to a different Energy Plus is because we wanted to have a system that can handle dynamic exchanges of energy between rooms, where the previous one was static and it was not very useful. But nevertheless, we did this for the behavior. We had the structure of the system. Here are the variables which go into insulation of windows, of walls, and so on and so forth. You can see it starts getting more complex. Again, you have numerical criteria and logic criteria. Okay, all right. I'm boring you with this, but I want to tell you that there are equations behind it and numerical optimizations that you have to do. And we did it. And here you see an expression of how many of these constraints are satisfied in simulations. The red ones are not satisfied, the green ones are, and you progressively go and satisfy your constraints. And you say, I have a feasible design. The lesson here is that we cannot talk about optimal systems because you have many criteria and many constraints. So the only sensible thing to talk about is trade-offs, and you are using optimization as a tool to do trade-offs. And you have to do it both in the logical domain, in the optical, in the classical sort of calculus-based domain. Now we're doing something else with Siemens product life management software. We try to take sections of buildings and try to address a very large market, which is how do I take existing buildings and change them with a minimal cost to make them more energy efficient. Okay, that's a much bigger and more difficult market than existing buildings. Another area where this has come up very strongly recently is the area of smart manufacturing. So in a sentence, what's the problem here? We have a lot of companies that they design prototypes, but they cannot manufacture, like medical devices, sensors, and so on and so forth, okay? So can I create the analog of a VLSI foundry for this kind of companies? Can I create a foundry where I can actually build, somebody will send me designs of medical instruments and in other domains, and I can produce them. So I want to separate design from manufacturing because that helps economically and gives a lot of impetus like it's happened in microelectronics. All right, so here is where you cannot avoid to study the interaction between humans and machines, because for these foundries to work in these multiple physics, multi-domain environments, you cannot do it just by the design of the production line itself. You have too many things playing around. So you need to have robots and machine interacting together. And that has led to industries that they create now things that are called co-robots or collaborative robots. And these are the pictures from these companies that they can now work with humans and do this small lot, as we say, manufacturing or test much more efficiently in terms of time, cost, et cetera, et cetera. And this was a program that DARPA started trying to create design of military vehicles in this way, where you design the vehicle and somebody else manufactures it. The program did not very well because the linkage between this design and manufacturer was not very good. Okay, it was nothing wrong with the method. It's just the linkage and the implementation was not very good. Okay, and another area where we had success, where my student who went to Facebook and now he has his own company, he created a complete environment for model-based system engineering for wireless networks, okay? So you all know that you have wireless networks almost everywhere. So how do you design them? So he developed a model-based system engineering environment, the tools, the simulations. We have several papers on this. And he has a library of components for sensors, different models, which can be improved as you learn more about their behavior. We created special, if you like, simulation tools, and this is available if you're interested. So I show you here how many things went to these environmental models. mathematical algorithms for trade-off analysis, modeling of the physical devices, okay, and the sensors and so on and so forth. And we're pushing this now to, if you like, DoD type networks, where we have many types of sensors, and we try to create model-based system engineering for autonomous wireless sensor networks, where you can see here, they may be vision or other sensors, they have different fields of view, and you try to combine them. And one new thing here, which is difficult, is in the behavior you want to capture autonomy. What does this mean, right? How do I quantify autonomy? How do I measure it, okay, and so on and so forth, okay? So very challenging problems. This makes noise, that's why I'm skipping it. But we're doing this with my current student and with Lockheed Martin and the Navy to try to do this kind of trade-off analysis for large networks so that several of the components are reusable and you can do the same kinds of things and provide guarantees for performance. All right, so you can see some of the simulations here of how the sensors move around and what they do. All right, since Srikant is in the room, we applied this also to design of communication networks. We had a lot of success in trying to develop tools for designing MANES first, and now we're moving to 5G and 6G and so on and so forth. Much more difficult problems, although some of them become easier because of the selection of protocols that have happened in the last few years, especially since most of the networks now become virtual. Okay, so but here there was an early success where we componentized the routing algorithms for MANES, all right, because we found out that that's the only way we would actually compare them. And we had several patterns of that where we showed these are the fundamental components of mobile ad hoc networks. And by designing them carefully, you get performance that you can guarantee. And this is a proof of it where in a key problem of the Army where the wired network separates and then you have to put them together with the help of UAVs and so on and so forth, we were able to get this kind of performance with our tools. And this was the previous best, okay? And that involved algorithms for using information from neighborhoods and estimating the topology, right? And this went into this design, okay? So, and protocols and so on and so forth. All right, so a current problem that we are addressing, which you all know is the so-called digital divide, where many people don't have broadband, and we try to bring together wireless communication networks, UAV and satellite networks to try to maximize the number of people that have broadband access at a lower cost. And this, of course, we are collaborating with some of these gigantic satellite constellations that you may be hearing about. Okay. All right, then this is the 5G vision that still is a vision because although many people say that we have deployed 5G, we don't have many of them. There are problems here in terms of the management of the 5G and trying to allocate so-called slices that they can satisfy the requirements of delay and bandwidth that various applications like autonomous cars or healthcare or manufacturing have. Okay, so the word that is used currently is network as a service. That means you take the entire network and you virtualize it. This is almost done in terms of core networks, thanks to advances like software-defined networks and network function virtualization, but the extension to wireless and 5G is not so easy. Okay, so, and then we want it because we have seen these reports that they tell us how much you can benefit if you if you have connected smart cities and so on and so forth. All right, these problems are still difficult and they are very big in scale and heterogeneity. And you think about the smart city, we have these 4 components: an operations center, a cloud data center, an IoT network, and a communication network, at least abstractly. And you can start applying these ideas to do model-based system engineering for this kind of networks to serve a city. And the key, of course, here is the slicing mechanism. And this is the depiction that we got from the source and GMN that shows you that basically what slicing is creating dynamically subnetworks that you allocate to particular group of users, okay? Now I want to go through some details to some specific things. And the first one I want to apply is model-based system engineering to some simple problems in robotics. Why I'm giving you this is because by no means I'm going to claim here that these methods and the problems have been completely developed and solved. I'm just showing you a direction with some promise of success. And I want to show you what we have done when one wants to go a little bit deeper. So this is a model-based system engineering applied to robotics, where most of the work of designing robots is basically case by case, and is what we call bench stop. You go to the lab and you start putting these pieces together, and then you see if they're satisfied or not. There is more recent effort to try to do this by the same way we do the aircraft, right? And that's an example. For instance, how do you design this arm? How do you select the geometry? How do you select the materials? Do you have 2 fingers or 3 fingers? How much of that is actually classical optimization and trade-off analysis versus machine learning, and how you can actually use knowledge, representation, and reasoning that is more part of AI into this kind of systems. That's what we're working on right now. And this is an example of success for a small robot that was designed by one of our colleagues using smart materials. And it was a small robot that was supposed to walk, but then the interplay between the controls and the materials was not possible in this bed-stop design. And the robot, instead of just falling the ground, occasionally would jump because there was some not good match between the control algorithms and the computers and the material. So with my student, Yu Chen Zhu, who's now at General Motors, we redesigned this. This is a movie of what my colleague Sarah Bregebrey, who's now in CMU, designed. It took about a year and a half to do this. And then within 3 months, by putting control together, and doing the mathematics and put them all together in the context I described and the Modelica model, we were able to fix these problems, change the geometry of the legs to be more like crab legs, and change the material. And I don't think the simulation would be fair. It worked pretty well. It went on the ground. It was not having this instability and so on and so forth. Okay, very small problem compared to what we have to do. But today we are working on, many people working on soft robots, different interplays between materials and geometry. Haptics are an important part. How do we put all that together? These are, here you see the fact that in another problem where we try to understand how you do model-based system engineering for a grasping, so that when you grasp a cup and you start pouring something on the cup, it doesn't slip. And you want to do it honestly in the sense that the cup is not just glass where you can squeeze it, it's plastic. We did the same thing. This was a master student of my student, Charles Meehan, who's now going into PhD in these areas. These are the block diagrams of the shadow hand, which is a very expensive robotic arm. These are the timing diagrams again, okay? We did the trade-off analysis of different criteria, 2 fingers, 3 fingers. And this is the one diagram that people use to show you the trade-off when you have multiple metrics, which design you're going to pick. And you see that not everywhere the maxima is on the same color, right? So you have to do trade-offs, and you have to pick things when you do these designs. And here's a movie of that I was also gave the talk in. Here is a movie of this design. After we did it by simulation tools, like you see on the left-hand side, we went and did it in practice, including the plastic cups and so on and so forth. Okay, I want to go on because I want to get you something that has to do more with AI. So now we have the ability to use printing and construct these hands and arms locally, right? Which is full democratization of manufacturing. And this from a company that can give you software that can make this kind of grippers or this kind of grippers or this kind of structures, depending on the trade-offs between weight, flexibility, sensing, et cetera, et cetera. Another difficult area is multi-agent systems. How do we apply this kind of methods to anything that has to do more than one agent? When in my group, when we discuss multi-agent systems, we use several multi-graphs. One is the collaboration graph on the top and the communication graph on the bottom, and in the middle we have the information graph. And the most important and interesting problems is in the interaction between graphs. For example, you study opinion dynamics in a social network, and you want to understand what is the best topology down here in terms of exchanging information so that the opinion converges fastest. Okay, there we proved, not by simulation, that small wall graphs in simple examples are good. And then we went to expander graphs, as I will mention, that there is something that information theories invested many years ago. Then they abandoned it, and then the mathematicians took it and proved that these communication graphs have many nice properties like fast diffusion, fast caching and all that stuff. So this is the example from the small wall graph that people controlled it by simulation. If I add 10% shortcuts, I get 10 times faster. We proved this by using randomization methods. And then this is the slide I use for expander graphs. They go back to 73. And the mathematics that you need to know is that there is a coefficient on expander graphs. That is the Ziegler coefficient that connects to the second eigenvalue of Frobenius. And that's why this has importance for speed. Now we can construct them easily. Pinsker called them magic graphs because he could not construct them. Gallagher used some of these things in his thesis on LTPC codes. They look like this. They're basically, this is expander graphs that Ramanujan studied. They are locally rich and globally sparse. And the people at Bell Labs do that when they were laying down cable for telecommunication networks, okay? And we're trying to find optimization criterion that each solution will give us as as an architecture of a communication graph that's close to expanded. In other words, we're looking for a communication cost. We are close, but we don't have it yet. Okay. And we use this to prove that the so-called instability of platoon in autonomous vehicles is not a problem. The problem was in the formulation, because all the papers you read in this problem is they allow only nearest neighbor communication. And if you know anything about wireless networks, you cannot restrict to nearest neighbor communication, wireless communications, right? You go a little bit further. So my student, Anup Menon, who's now in Waymo, we saw that if you allow a simple extension of this nearest neighbor to nearest of neighbors, the problem is completely stable. And here is the result. Okay, you get very good results, both in terms of all the criteria you have, the communication load and the stability margin. Okay, then we went to other problems that have to do with what is the simplest possible communication you can give and get still simple algorithms that they converge to social optima, or it's called system optima. And here there's a whole sequence of works that we did in wind farms, in sensor networks, and all kinds of stuff. And this went to the behavior, right, of the model system, because again, this has to do with what the system does. Okay, and we found, and other people worked with that, like Marsden, and on simple models that they give you local optimal. We proved them, and we proved also the convergence. We have done similar things, since the topic is social networks, for social networks in terms of trust and mistrust. And then we did this similar studies for security, where I don't know if you know this, but the biggest problem in security right now is we don't have a provably composable security theory. Meaning, if you take components and you made them secure, if you put them together, then all the theorems we have say, unless you have some third structure to give you something more, the resulting composed system will be not secure. And one breakthrough that we have here that looks to be, promising is, and we use this for cars and so on and so forth, is allocate some of the security methodology to the hardware, or what we call the physical layer, okay? And that means you have to use properties of hardware, like the trusted platform module. Most of your computers have it, and most of your information technology managers, your universities, organizations don't even know that the technology is there, so they don't use it. Please try that on me. We use secure biometrics, where we saw that in many biometrics, when you extract the biometric, you also extract a signature of the sensor. So I can attest that the biometric was taken by this particular sensor, so you cannot break it. And the latest thing that you may have heard is that I can go back to the old idea in wireless networks of time pads, and I can use the randomness of the channel to be able to show that the unbreakable time pads actually work in wireless, because you don't need to have the two major restrictions that Shannon pointed out, that you have to have, a very strong transfer of the keys from one person to the other, and very strong keys. These go away if you use this kind of randomization that is inherent in wireless networks. And I can go on and on to show you that some of the things we do in control, communication, and so on and so forth, they help here. This is an example of how Bosch changed their controllers and the filters at the hardware level because of the experiment that was done in the West Coast, that people got into the car by the informatics network. And then because once you get into the network of the 140 chips that the car has, you were friendly to everything. So then we had a workshop on that in Maryland about 4 years ago. And then people realized that now I have to have special policemen for every one of the chips, right? And that's an answer from Bosch, which is a major manufacturer. Anyway, and then we apply this to the componentization of routing protocols. Another area where this has been applied, now I'm going to go fast, and Max is not going to be happy. We apply this to learning robots, teaching robots, and the safety that is important. And there we actually introduce contract-based design to try to handle these problems. And then we went to systems biology, which is a version of system engineering for biology. It's the toughest of them on. Actually, one of the languages that people use in system biology, which system biology is a derivative of SysML, if you like. And we did models with my student Christine Rose, okay, on the modeling of Alzheimer's disease, where we use 3 interacting networks: the blood network on the brain, the neural network of the brain, and the chemical network of the brain. We ran this. She validated these networks in mice. We ran them backwards, and we found the fact that you can have, at least in mice, And then it was verified in humans. It was known you can have a disease for 20, 25 years, and the sensors of these small alpha beta plaques, you don't know them. We try to do several therapeutics, and we can use these models to prove that it won't work. This is still ongoing work. And then we did management of intensive care units that we had a big problem in Maryland. You look at the set of hospitals and you try to manage the allocation of resources, means doctors, nurses, and instruments to trauma people in 13 hospitals. So you try to minimize cost and delay, all right? And we also build a model for massive diseases like diabetes by using stochastic control and building an information system of the likes that exist in Finland and Massachusetts, where you can have all the major hospitals connected, a majority of the medical practice connected in the individual. So you can go and ask questions like, what's my status? Based on my data, I'm a pro-diabetic, I'm healthy. What should be the next test I can do? And what should I be okay? Do I need to be tested? And so on and so forth. And this used control of multi-agent systems, but it used also some of the models. Okay, so let me go to the final thing. And this has been also used by us and others in the Wyss Institute in Harvard to try to do chips like that they have hardware components, software components, and in vitro cells of bodies to try to understand the side effects of drugs with different people with different genomics. Because the pharma industry wants to go from one drug for everybody, which makes the testing very expensive, to subclasses of drugs classified according to the side effects. They claim this is going to cut the cost and time by 5. All right. All right. Where is artificial intelligence and that? This addresses the last challenge I told you about how I connect databases. Okay. So this is joint work with Park. And we exploited the fact that we have one language, which is Modelica, that models all chemical systems, physical systems. And we now can think of a system as a sentence where the words are the components. Okay. And that allows us now to create libraries of components, which are, of course, translated to Modelica models. And then we can use natural language processing tools to answer questions like this. If a component is missing, what's the best component that I can put there so that I get certain result of the system, which is the well-known simple artificial intelligence problem of the sentence completion. Okay. And we have here various examples of how things like electrical circuits or things that are Port Hamiltonian can be compared by regression to functionalities of the components that we do not know and classified according to them, and then find physical structure of them and bring them into the design of the system. Okay. So we have several papers on that with Park that we do things like type discovery of components using this Port Hamiltonian framework, trying to find which ones are accurately classified. And you can see here the easy ones are resistors, conductors, and but once you get into more complicated components, the methods we have right now are not very accurate. And these are for mechanical Modelica components. This is against the library of components that exists already in Modelica. Okay. And we went around and did this model parsing, developed a model which was like a circuit, which is true for chemical, mechanical, electrical, another thing. We went to a graph, we took the graph, we spring it out the string, we went to these sentences, and we were able to find completion of components, like you see here, and prediction of what models we used. So this is a first step towards linking to databases of heterogeneous representation and try to bring them into the equation. And then there's another issue that we also have tools and analysis. When you ask design questions, this is a query, and the tree query has an exponential depth. If you want to make it linear, you have to group the queries that they are related. Okay, so you can think of them as factographs, but anyway, once you do that, you can see that you can actually change the exponential tree width to linear, and then your queries are faster and much more efficient. We have developed this tool, we have the theory, several papers, and we apply it to the design of quadrotors, for instance, right? Where we actually exploit the connections between the specifications to try to ask questions in groups and not individually, right? That's a nice other special case, okay? So I'm giving you a special case of small steps to where we want to go. And again, I repeat, by no means I'm claiming we have the answer to everything, right? It's just, we think we have right directions, okay? There are, of course, still issues with machine learning and artificial intelligence, and I want to close with what we mean by these things in Maryland, at least in my group, okay? And you may have seen this. There are three challenges before, if I'm in the audience, that I will not ask you what you mean by artificial intelligence. The first thing, we're working on mathematics of deep networks, and other people do the same, but we also work on mathematics of non-conventional computation, like neuromorphic, and we try to put together so we can do with these architectures, which exist, do both numerical and conceptual, if you like, calculations. And we call these universal machine learning algorithms. And then the big gap here is that you need to also study knowledge representation and reasoning. Because if you think how you learn concepts, you connect them, you compact the knowledge, you use a conditioning for new things, right? So there are two major methods for this. One is knowledge graphs, which is very well known, and it's the same word as ontologies. The newer one is semantic vector spaces, which got a lot of prominence because it was very useful for natural language processing. In natural language processing, they integrated knowledge graphs with semantic vector spaces, and many people claim it was this integration that gave you some of the products you enjoy, like automatic translation and other things. I do not know of any other data field that this has happened. We're working on that, especially in the area of intrusion detection for security. So you have a universal machine language, you have a universal model for knowledge representation and reasoning, link the two in the sense that you can use these linkers to compact your knowledge and use as conditioning as you keep progressively learning. And then you can call this artificial intelligence, or if you like, the term I like more these days is augmented intelligence, okay? And then you have to ask the question, how do I link all that with the revolution in hardware that's happening in terms of non-von Neumann chips, like you see here, the Loihi and others? And then how do I go between hyperdimensional computing, again, which has hardware and deep learning? And how do I go to things like hierarchical temporal memory, which also has hardware that has advantages over deep networks? And how do I translate whatever part of the system engineering, either the tools or the components, has to do with machine learning and architecture with this hardware? These are all open questions, but wonderful questions, okay? And this is what we're trying to do in my group. And now, let me tell you my political, if you like, statement at the end. I don't know if you remember that President Obama started this democratization of manufacturing by these huge institutes on manufacturing, where the idea was precisely to go from ideas and tools to making things, okay? And this led to a lot of companies creating so-called maker spaces, where people can go over the weekend and make something by exploiting printers and all that stuff. In Sweden, we have a school in KTH that we can pass 50,000 students from elementary to high school students to do this like that. Google started and finished now the Google Project ARA, where they design from beginning to end a smartphone with these tools and everything, in the manufacturing and everything. And Ubuntu did the same, okay, by these tools that I'm telling you. And you have, many other ideas. We're not going to succeed in this and be competent, either worldwide or as a nation, if we don't change the way we educate engineers. And you've heard that more and more people are getting into classes which are hands-on. People have to make. But I want to tell you that my view is beyond makerspace. That's why whatever we do in this area in Germany, Sweden, and here, I call it the I makerspace. And the I is for information. I want to use these information tools that I described, or simpler versions, to design first in the virtual world of simulation, emulation, and design tools, and then go build it. Because this way you learn how to argue, and also you have higher success to design things that they work in a little amount of time. And we have a master's in system engineering that would do these things in Maryland, in the Institute for System Research. And for those of you who think these things are very hard, here's my answer. We're teaching this course since 2010. It's a hands-on project course that gets students from all over engineering. It's oversubscribed every year, and we get 60 plus students every year. What they do is we give them about 12 lectures of the tools, and then they make groups and they go through this process. I'm telling you that because these are not difficult things to teach, even if you allow me to say that in a simpler version of these tools, okay? And we have to understand what the Technion told us in the beginning of 2000, how to educate centuries in this century. You have to understand that there are two classes of engineers or scientists, or at least applied scientists. The ones that they design the tools and they need to be educated differently, and the ones that they use the tools and they have to be educated differently. Okay. And I think this is as big a revolution as the ones I list here. Typography revolutionized, if you write something, you could print it. You didn't depend on the person who had the printing, and they could stop your book or ideas to get published. Microelectronic chips. VLSI separated design from manufacturing. So if you were a big company, you had the factories, you can no longer stop me from making my chips. The PC gave computing power to everybody, okay? And the internet gave information, good or bad, to everybody. And I think these tools of integrated model-based system engineering and database methods, meaning putting it all together along the direction I pointed and finishing this vision, has the ability to democratize manufacturing, design, the way we treat social networks, the security of social networks, many, many, many things, and their health and other impacts, okay? And it's already having impact as big as the other four. And thank you very much. These are some references I have in the lecture. I'll give the slides to Manxi, and I have to tell you where you can find me. Here's where you can find me. If you have any questions, criticism, collaborations, you're all welcome. Thank you very much.
Thank you, Professor Baras. So I think we have, okay, so we have a question from David. What's your point of view about dynamically managing the electricity power supply distributed to buildings and inside the buildings of departments that make it up? Could the MBSE be used to design a kind of elastic power supply capacity?
Yes, as long as you give me batteries. Okay, so the fact that we now have wonderful batteries gives us the flexibility to make even locally sustainable and survivable microgrids. And one lesson we learned with all these studies is that what the Germans say, you consume energy where you produce it, because the transmission cost is huge, and that has actually created a lot of problems with things like wind farms. But in photovoltaic, there are huge programs from the Department of Energy that I review, and I know what's going on. And the acceptance of photovoltaics, even in small groups of neighborhoods or households or small grids, is becoming more and more realistic and much more elastic, thanks to the fact that we now have batteries that we can store electricity, and we don't have to store it by selling and buying from the utility company. Is that close to what you were asking, or I missed it? There's a question and answer here.
Yeah, so I think David said absolutely this answered.
Oh yeah, okay. One other thing I want to add is that okay, I see what another thing. So machine learning can be used to learn the patterns of demand, right, in different parts of the electricity utility company. And that we use, and also try to learn what you can deliver, because you have uncertainties with respect to the supply of renewables, right? And then you can use these two and make them as constraints, dynamic allocation. And that's used both in smart grids and also in wireless networks, because you have similar problems. And it's impossible to develop analytical models. Or even if you have analytical models, you can supplement them with data models and make them better.
There's another question on what about data-driven system to generate modeling?
Which one?
What about data-driven system to generate modeling? So this is from Stefano Bonfa.
Okay, my answer is very simple. I think you need model-based and data-based working together. I can give you many examples where one or the other is in deficiency in difficult problems. Okay. In other words, to put it simply, we should not forget everything we know in engineering and physics and go complete data-driven. Okay, because quite often we don't have enough data or enough computational tools to develop the models we need. And even in simple control problems, recent results have shown that if you forget your theory, let's say linear quadratic, and you try to learn the controls from data, you end up with very brittle problems. On the other hand, from theory, we know how to produce robust controllers. So you should not give up what you know already. I mean, like the good theories you have, but you should supplement them from data. That's my view.
Yeah, thank you. We're a little over time. Is there any other questions from the audience? Okay, so I have maybe I can ask my question quickly. So I'm curious, like when you extend this modeling and the prediction, both prediction and control models from in like manufacturing and control and dynamical systems to societal networks, that the incentive and strategic behavior of their human users are playing a greater role. Like, what kind of new tools that you think will be important, and how you see this being integrated?
Very, very good question. There's a very big gap in the science of these things. There are two gaps. We do not understand very well human behavior and human decision making. We are doing work in this area, which is another long talk, and several people are trying to understand that. But the other we need to understand and put into this, and we have done it a little bit with robotics, is intent. How do you model my intent? Okay, and how does the robot understand my intent? Okay. And there are models like that have been developed by roboticists, but we have not put them here yet. And this is key to get efficient and flexible human-machine collaboration, right?
Right. I guess the challenge both is
it's missing. It's missing.
Yeah. I guess the challenging both comes from like the lack of data, of like the sufficient amount of data to accurately predict the human behavior in this complex system, but also about like humans' behavior change when you impose a control systems or a decision of the dynamics that kind of makes your old collected data may not be transferable completely.
So my answer to that is very sharp. I don't think you should expect that you will get enough data in all the problems you want to work on. Okay, so you need to develop systems that they can start learning right away with as much data as you have, and use this knowledge representation and reasoning to try to improve both your machine learning and your understanding of the problems, right? And create this representation of knowledge that you can use for conditioning. And again, all I'm saying is that I believe very strong common sense, because if you think how we humans learn and how do we act, we do this, right? When you learn different things, you connect them, you find relationships because they help you. And the other thing is, there are time scales in the problems. When you drive, you don't analyze all the time the entire scene. Okay, you have recipes that they work well on some phenomena you observe, and you apply them because you don't have time to analyze.
Yeah.
So we need to get to this kind of systems and put them in addition. We're trying to some extent to do that by adding temporal logic constraints and this kind of tools into the tool set I described, okay? To try to handle things like collaborative robots, humans and robots, teach robots and stuff like that. But again, that's the beginning.
Right.
But please do not, please do not develop only specialized tools. Try to create some framework that is common to many of these problems. This is my last words.
Yeah. Thank you. Is there other questions from the audience and the panelists? Okay, thank you. Then I think we can conclude this seminar.
Thank you very much, everybody.
Yeah, thank you, John. Thank you. Thanks, everyone. Yeah, thank you.